Okay, so page 22, question 4. I know that I got a few questions about this one, and most of you probably have this down already, but it's still worth making sure you understand that one. So 5 boys and 6 girls sign up for a trip, and only 4 students will be selected to go. Determine the probability of the following. Only boys will be on the trip. So before we even answer this, right, you're on an exam. There's the 3 things I always want you to ask in this unit. Is it probability? Is it odds? Or is it just a number of ways? Okay? In this case, it does say it's probability, so you know you're going to have to stack 2 numbers. Chances are, guys, don't quote me on this, but it's going to be worth 2 marks if it's like quite a bit of work, right? You need to find NU, NA, stack them, right? So it's going to be more than just 1 mark if it's this type of scenario. Also, we're just selecting 4 to go on this trip. The order doesn't matter, right? Whether I select, right, a student first and then a next one, it doesn't really matter. As long as you get selected, you get to go. Does that make sense? So order does not matter. Is irrelevant. Okay. So this is comms. A nice thing is, I'm going to follow up with the province. I emailed, there's always a person we can email about this, but the reality is if you pick perms or comms, and if it's a probability scenario, you will get it right either way as long as you're consistent. Because it kind of cancels out, you know? Because with perms, order matters, so the numbers are going to be bigger. With comms, the order is the numbers are smaller because you don't care about order, right? But they end up canceling each other out when you stack them. So that's kind of like an interesting. Some of you is like, oh, I got it, right? But oh wait, I used perms, you used comms, you got the same answer. Like what's happening there? I'm just going to ask the province, is that okay? As long as they arrive with the correct final answer. But if this had been determined the number of ways to select only boys on the trip, then you would have to select combinations or else you'll get it wrong, okay? Because it doesn't cancel out in that case. So A, only boys on the trip. So let's see here. It wants probability. So NA for me would be 5 choose 4. And from the 6 choose none, right? And the NU would simply be, you want to just consider the 5 and the 6, so that's 11, right? 11 total. So I just want to choose any 4 from the 11. And I have the numbers here. So you get 5 if you do this right. 5 times 1 is just 5. 11 choose 4 is 330. Oh, I thought you had a question. So probability is 5 over 330. And if you reduce it, it's 1 over 66, okay? B, there will be equal number of boys and girls. So the only thing that changes is NA. NU stays the same, okay? But for NA, it's going to be from the 6 choose 2 and from the 5 choose 2. There's an equal number this way. This is the only way that can happen. There's no other way. And so 6 choose 2 is 15, and 5 choose 2 is 10. So that's 150. So if you do your probability, it's 150 over 330, which reduces to 5 over 11 if you did that right. Okay? Either way is fine. Either way is fine. C, there'll be more girls than boys. There are several ways this can happen. This happens, I will actually write it out, when there are 3 girls or 4 girls. There's 2 different, there are 2 different scenarios you need to consider. So that's the question I got yesterday. When is it and? When is it or? When do I multiply? When do I add? Okay, I need you to pay attention to this part, okay? here, for example, when we went to the first one, only boys are on the trip. From the 5, you choose 4, and from the 6 girls, you choose none. This is happening simultaneously. That's the one case you're considering. That's where it's times. Or for the second one, there will be an equal number of each. It's still saying you need to choose 2 from the 6, and you need to choose 2 from the 5. So that's multiplying. That's how we come up with this. C is there's more than meets the eye. You need to consider this case. This is case 1. And this is case 2. It's like you're adding the cases. You're adding. So there will be some multiplying under each case, but you need to add those results to get your true final in A. Does that make sense? Or so I'm going to consider this case. From the 5, choose 3. If I choose 3 girls, then from the 6, I must choose 1 more from the boys group, right? This adds up to 4, adds up to 11, so we're good to go. This is case 1. The other one would be from the 5, choose 4. From the 5 girls, choose only girls, so that'd be all 4 there. And this is irrelevant. This part is not needed. But the problem is if you forget about that, if you go back to this scenario, you might not think of it. You might just go 5, choose 3 and just leave it at that. That's a problem, right? You need to have this part that goes with it. 5, choose 3. Let me just get this right here because I did it slightly differently on my key. Did I mix up? Yeah. Here, I get this wrong, right? Yes. Thank you. So this has to be 5. Thank you. I was just checking. You don't even buy it anymore. It's like, no, we've seen you do pretty bad mistakes. This was a legit mistake. Yeah, it was. My bad. 5C1, 6C3. Now we're talking. That is 20. This is 20 times 5. And this is just 1. So 6 choose 4 is 15 times 1. So this is 100, and this is 15. You need to add these, okay, to get 115 cases, like favorable outcomes that we need to consider. So your probability would be 115 over 330. Okay, that is, so this one would definitely be, in my opinion, this would probably be worth 3% from the province perspective. They would probably give you half, and then 1 for adding. That is important, an important concept to know that you need to add, and then 1 more mark for stacking. Okay. So yeah, there's a lot involved. Are these very common? Not so common. Okay. What I see more when it's like cases, that they will ask you how many groups can be selected where there's more girls than boys, then they would want the 115. Okay, turning this yet going further into a probability is less likely to happen. They might break this down and then ask you to stack. It's up to the province, of course. But anyways, so let's go to 5. Any questions about this? Any further? Okay. Let's go to 5. This is where I even got a little bit like, did I make a mistake? Okay, is the book wrong? Like, what's going on here? You make passwords, and it has to have 2 capital letters followed by 3 digits. We're okay so far. For each of the conditions below, determine the probability that the password chosen at random will contain the letters S and Q. Okay, it says and, so they both have to be present. It doesn't say S or Q, it says both. So repetition is not allowed in the password. So let's do A here. This is the biggest part, universal. What is the universal here? Letter, letter, number, number, number. Okay, so what would you say is your universal? I think I posted the key, so if you check the key, you will know. You would think it's 26 times 26, right? But it's not. It's 26 times 25. Why is that? Because it says repetition is just not allowed, like it's not even an option. Okay, that is why, because of the statement made here. So it should be 26, 25, and then these are numbers, right? So it must be 10, 9, 8. So that's how you do that part. So that would be a total of 468,000 passwords. It's not allowed. So NA would be, this has to be S or Q, S or Q. Like the order doesn't matter. It didn't say S first, then Q next. Okay. So this would be 2 times 1, and this would be 10, 9, 8. And that would be 1440. So here you stack your numbers. 1440 divided by 468. Oh, order matters. I hope you understood that order matters here because it's a password, right? Like that one is hopefully very obvious. If you reduce this, you get 1 over 325. I'm just going to leave it at this. This is correct. If you turn that into a decimal, you'll also be able to see that it matches. Don't look so excited, guys. NA. Repetition is allowed, so it is now an option. So that's where NA would be. You have to be careful. This still has to be SQ. But can you go 2 times 2? I would say the answer is no, because if you say 2 times 2, that means that you can have SS or QQ, which violates this requirement that you have to have them both. You have to have them both, so this has to be 1. But repetition is allowed, Mr. Dirksen. What's going on? There's a lot of things going on here, okay? So this would be 10 times 10 times 10. So the numbers, no problem. You get to reuse if you want, okay? So that would be why do I have 4,000? My key has 4,000. Oh no, I changed it to 2,000. Yeah, I changed it to 2,000 at the final answer, but not along the way, so my bad. So it's 2,000. NU, now you get to use 26 there, 26 there. 10 times 10 times 10, okay? So now that repetition is allowed, the universal allows for repetition, okay? So it's 676. The probability is 2,000 over 676. So the question was, Mr. Dirksen, I thought the universal is the same. It's 676 here and here. And the reason that it's not is because repetition is just not even an option. The website, literally, if you were to repeat characters, the website would be like, can't do it. Got to find something else. It's not even an option. So the wording is a little tricky. This is all textbook stuff. Textbooks, they are known to try to mess with, really try to get you to think, right? Not necessarily exam-worthy questions. Like too many things going on, now we're trying to trick you, and if you get it wrong, it's just a nightmare to mark, okay? So not necessarily an exam question. Okay, now I'm going to pause here. Any questions from the floor? Strongly dislike this question. There we go. That's better. Don't hate, Mr. Dirksen. Don't be hating. Yeah, so this question I don't like because they give you specific positions. So what do I always tell you? Perms, right? But they want Tara and Laura on the team, determine the odds in favor of Tara and Laura being chosen to play in the infield. And the coach decided to choose who will be the 4 infield positions. We just care about the 4 infield positions, not necessarily these ones, right? And Tara and Laura are on the team. It doesn't say Tara and Laura are first base, second base, or whatever, right? Like, it doesn't say anything about where are they specifically. So ultimately, it just cares about being on the team. So I will make a note. I hate this question. Can I put that? I would not do that to you. I'm not going to do that to you. The province won't do that to you, so you don't have to worry about it too much. But I will say this. Although positions are mentioned, we are only considering being on a team. And you can also say Mr. Dirksen hates this question. That's okay. Okay. And what I like about this one is that we're not asking for probability, we're adding for odds in favor. Tara and Laura being chosen to play on the infield. What does that mean? It means that we're going to figure out NA. In favor means that you want the event first. And on the other side is what? N, not A. Do you remember that? It's never total, right? There shouldn't be an NU here anywhere. So I will, by the way, this notes, I will say therefore combinations. I will put a little twist on this. I will say that, let's figure out NA here. Tara and Laura are being chosen. So from the 2, you want to make sure you choose the 2, as weird as it sounds. How many players are still left? We have 9 in total, right? 2 are gone. So now this is 7. Choose. I need another 2 for that. This is Tara and Laura. And this is the others. Notice that the 2 and the 2 still add up to 4. Okay. And the 7 and the 2 add up to the 9 total. Okay. So this is it. So this would be, let's see here, 1 times 21, that's 21. That also used to be a big deal, right? Were you too young for 21? I couldn't say it. Like every time I said, Anyways, 21. I would recommend, okay, listen carefully for this. I would recommend to find the not, I'm going to find the universal. So universal is what? From the 9, choose any 4. That is 126. So in a sense, I'm doing the same thing as probability here, guys. Do you see where I'm going at? So I'm going to go 21 compared to what goes on the other side. The rest, right? So I'm going to go 126 minus 21. So it's 21 to 105. And you're done. Okay. If you want to reduce this, you do it the exact same way as a fraction. You go 21 divided by 105, and then you go math fraction, and then it's 1 over 5, and then just state it like that, or 125. Just make sure you don't turn it into a fraction, because then it's wrong, right? But you can reduce it the same way. Alternatively, just find a number that fits into both of them and just divide it by that number, and then you can reduce it that way. You can do it several times until you get to the smallest. The only reason I would want you to know how to do this is if the answer would be a multiple choice question, right? And you had to pick one of them. Could you turn this into a probability? I need you to know that probability would have been 1 over 5, 1 over 6. I'm not going to circle this because it's not my answer, but this is how you would go to probability. Okay? And so maybe that's going to help you determine the correct final answer, because you can turn these into a decimal and then compare all your odds, turn them all to probabilities, figure out the decimal, and then pick the right one from that list. Okay? Any other ones? Yeah. 9? Oh boy. I hate that one too. No, I appreciate that. I appreciate you guys asking questions. Any day. Okay, Leslie needs to create a 4-digit password to access the voicemail. She can repeat some of the digits, but all 4 are not to be the same. Determine the probability that her password will be greater than 5,000. You know what? A is not out of the question, okay? Question A. So let's do NU, because then you're halfway there. NU would be, does order matter? It absolutely matters. NU would be 10 times 10 times 10 times 10, correct? But are we allowed all the passwords that are generated here? Are we allowed all of them? We cannot have all of them. That's, by the way, that's 1 followed by 4 zeros. That's not quite right, because we cannot have this. We have to remove them. So if you make a note, we cannot have, so example, we cannot have 0, 0, 0. We cannot have 1, 1, 1. We cannot have 2, 2, 2. We cannot have, this keeps going until you get to 9, 9, 9, 9. You cannot have this. How many passwords are we talking about? 0. There's 10, right? Yeah. There's 10 of them that you cannot have as part of your options. It's just not allowed. So we're going to go minus 10, and it comes right from here. So that's 9,990. It's because of that you cannot include it. And for NA, let's do that one next. The probability that her password will be greater than 5,000. Let's see here. What is allowed at the front here? If you want greater than 5,000, would you consider 5 as one of your options? But what if it's 5000? Then it's exactly, bless you, then it's exactly 5,000, right? But it says greater than 5,000. We'll worry about that later. There's only one number that we cannot include, right? So we're going to go, this. You can have 5, 6, 7, 8, 9 at the front. So how many is that? That'd be 5 options, right? And then you could have 10 times 10 times 10. So that would be 5,000. 5,000 numbers. But one of them is 5,000 exactly. The 5000. So I gotta subtract 1. This is the number 5,000 itself. Does that make sense? If I had, like, if I started this with 5, and this would be 0, 0, 0, okay? That is exactly 5,000. It wants numbers that are greater than 5,000. So I have to remove that. Okay? And I have to remove the ones that are all the same. How many are we talking about? 5, 5, 5, 5, 6, 6, 6, 6, 7, 7. So how many are going to be all the same in this particular circumstance? 1, 2, 3, 4, 5, right? There's 5 additional passwords that I must remove. All the same. So that's 4,994 because you take away 6 passwords essentially. Why do I have 96? Is that my bad? My bad. I think my key has 96. Probability 4,994 over 9,990. Was my key, is it because of my key that you're asking, Julian? Yeah, I was off. So that's right. Yeah, so that's my bad. Did you have the 4994 instead of 996? I'm not sure. So this, let me see, I'm going to check the key here real quick so that I don't mislead you guys. 9A. Yes, this is the correct answer. So that was my bad. It's if you look at my key, you would have noticed that it's my mistake, right? That's what happens when you do that on a Friday after school, right? Don't make a key Friday after school. Okay, B. Determine the probability that the first and the last digits of her password will be 4. If this is a 4 and this is a 4, I mean, you've now severely reduced your options. So there's only one option there, one option there. Everything else is game. So this would be what? 10 times 10 is 100. What's the only password that you have to remove, though, from the 100? 404, right? 4444. So minus 1, this is the one where you would have all 4s. Where this is a 4, this is a 4, right? You can't have that. So it's 99. I have to stop lifting weights. My pencils are always breaking. Or I need to get like, instead of 0.7, I need to get like 1.4 or something. If you find one of those, let me know. Okay, that's that. And then C, determine the probability of the first digit of her password being odd and the last one being even. 1, 2, 3, 4. Even, we're talking what? 0, 2, 4, 6, 8. So we've got 5 options here. This is 1, 3, 5, 7, 9. We've got 5 options there. Here we don't really care. So this would be 2,500. 2,500 altogether. Question, do we need to subtract any from this? Do we ever have to worry about all of them being the same? No, because if these are all even and these are all odds, you'll never have the same going right across. You don't have to worry about it. So I'm going to go minus 0. Okay? So that's 2,500. So the probability is 2,500 over 9,990. Sorry for the headache, but it gets you to think. I hope that's what this did. Any other ones? Okay. There are good ones everywhere. You know what? I want to do 11 and 12 for sure before we move on. Okay. Larissa tosses 4 coins. Determine the probability that at least one coin will land on tails. It says create a tree diagram. This is going to be tricky, right? But 4 coins, that's heads or tails. You've got heads, tails, heads, tails. So if you did 2 coins, there'd be 4 outcomes. We keep going. Heads, tails, heads, tails, heads, tails. If you toss 3 coins, you'd have 8 because it's 2 times 2 times 2. It's 8, right? One more. Why 4, right? Why do we toss that many coins? Stop tossing around. Heads, tails, heads, tails, heads, tails. How many are we talking about? Can we verify mathematically without guessing? You should go 2 times 2 times 2 times 2. That's 2 to the 4. That is 16 outcomes. That is, I would expect you to know, okay, 16 outcomes without a tree diagram. Let's double check. 2, 4, 6, 8, 10, 12, 14, 16. Did you know that you could do a tree diagram every time? Like the passwords we just did? It'd just be thousands, sometimes thousands of options. So it'd just not be feasible, okay? The probability of at least one coin landing on tails. So let's write this out. Heads, heads, heads. Tail, tail. Heads, tails, heads, heads. Heads, tails. Heads, tails. This one here is heads, tails, tails, head. And then it's heads, tails, tails, tails. Yikes. Tails, heads, heads, heads. Tails, heads, heads, tail. And then it's tail, heads, tail, heads. And then it's tail, heads, tail, tail. I'm off script here. But now it's tail, tails, heads, heads. And tail, tail, heads, tail. And then it's 3 tails, heads. And all tails. Okay, sorry about that. It's very messy. To be honest, it won't really matter in this case because at least one will land on tails. If you think about it, all of these ones, right, all of these options have at least one tail. They have at least one tail. So there's only one option where you have no tail, otherwise known as all heads, right? So what would you do? I don't think you need a tree diagram every time, especially if it's at least one. probability would be 16 total outcomes, and 15 out of those 16 involve at least one tail. Okay, so this is where I put the 15. The ones that have at least one tail in their outcome amounts to 15 over 16. I want to draw your attention to this one. Remember when it says at least one, like use at least one to make an outfit or a salad or something? Recall 2 to the n minus 1, right? So 2 to the, we're tossing 4 coins minus 1. That would be 16 minus 1, which is 15. Sorry, you can't see that because I'm zoomed in too much, my bad. So there's 15 ways to get at least one tail. So probability would just be 15 over 16. So you've got a visual way to figure it out, but you also have this to figure it out. Yeah. Chapter 4. That was the one before this, yeah. Keep going. Five friends, including Biljana and Bojana, are sitting in a row in the theater. So 5 friends, including these 2 people. Okay, so it's 5 in total. Determine the probability that Biljana and Bojana are sitting together. Does that ring a bell? Sitting together beside each other? That's the probability. So let's do that one. NU, let's just do NU. Does order matter if you're sitting in a row arranged? Order matters. We can write that down. Order matters. Perms. Okay. So NU would simply be 5 factorial or 5 pick 5. It's up to you. Or 5, 4, 3, 2, 1. That is 120. There's 120 ways to arrange these 5 people every which way. NA, do you remember how to tackle this one? These 2 friends are sitting together, so you put them together. 2 factorial, so you can move them. And then it's 1, 2, 3, 4. So I actually go 1, 2, 3, 4. So this will be 2 factorial times 4 factorial. That's 2 times 24. That's 48. 48 over 120. So restriction, no restriction. B, how would you do B? Them not sitting together? Universal minus them sitting together. Since we're talking probability, I mean, you can do it however you want. You can do it this way, where it's still 120, and then just go 120 minus the 48 ways that they're sitting together. What would that be? I did it differently, so 72 over 120. So this is one way of doing it. Or you turn this into a decimal. 48 divided by 120 is 0.4. So you could have just gone 1 minus 0.4, which is 0.6, or 60%. So it's either or. This gives you 60%, or just going 1 minus the previous answer and then get 60% that way. It's up to you. Just remember it's probability. And I lied to you. One more. Sorry, Anna, were you still copying? Go for it, go for it. I'm just gonna do 15. I'm not sure if you guys did that one. All right, let's cabinet. Erin has lettered tiles. She selected 3 of these tiles at random. Determine the probability that the tiles will be 2 vowels and 1 consonant. What's the probability of this happening? And let's do NU first. NU, you're selecting 3. Question, does order matter here? Selecting 3, does it give us any indication? So order does not matter, is irrelevant. So comps. Okay? So universal would be from the 7, choose any 3. I don't care which ones, just 3. NA, how would you do NA? What are consonants? What are vowels? How many vowels are there? 1, it's A, I, E, O, U, okay? 1, 2, 3. 3 vowels, and therefore 4 consonants. You're creating, you see what happened here? You're creating 2 subgroups here. You're creating 2 subgroups, so that's also happening at the same time. So we want 2 vowels. So from the 3, we're going to choose 2, and from the 4, we're going to choose 1, right? We got to have our 3 tiles, and we got to have our total of 7. 3 choose 2 is 3. 4 choose 1 is 4, so that's 12. 7 choose 3 is 35. So you've got your 35, you've got your 12. So probability is 12 over 35. That can be reduced, but I'll leave that up to you. Okay, I'm going to leave it at that. Enough is enough. Question? Question?